So chondrocytes making the cartilage. So these are the guys these little eyeballs that are looking at you. They're secreting their matrix, which consists of a lot of elastic fibers. Those tend to pick up a lot of black or really actually dark purple stain. So they appear black when you look at the tissue. So when you see all these stringy looking black things around the cells with the nuclei, the eyeballs looking out at you, that's going to be your elastic cartilage. Elastic cartilage is designed to be able to deform it, and then when you take the deforming forces away, it springs back. So ears, that's easy to see. You deform it, you let go, and it springs back. Doesn't stay crunched. Epiglottis, you don't see it because it's inside. But if you believe, and you probably know that if you swallow incorrectly, you get saliva down into your trachea and it's going to cough it back up. So epiglottis is supposed to close when you swallow and then spring back up when you go back to breathing. So those are places that you typically can experience your elastic cartilage. The auditory canal, it's bone way in, but if you stick your finger in your outer ear, you can move this canal back and forth. So it's got to be not bones, and it's connected to your auricles, so still elastic cartilage. Cuneiform cartilage in the larynx, if you've had anatomy before, you know it's a little tiny cartilage that is lateral, and a lot of textbooks don't even show it to you. They show you the corniculate cartilage and the retinoid and the cricoid and your thyroid cartilage, but since the cuneiform is in the tissue to the side, sometimes the textbooks don't show it to you, but it is helping to support the larynx laterally, the soft tissue laterally, but gives some flexibility. So you can change pitch by controlling the tension on the arytenoid cartilage, but you also are changing the tension around in the soft tissue with those the muscles that are changing the tension on your vocal folds. So cuneiform is helping with some of the stability and some of the transfer of, I guess you could say, your muscular energy in that voice box area. So it changes shape easily, but then as soon as the deforming pressures are off, you're back to where you started. Fibrocartilage, as the name implies, you got a whole lot more fibers than you do cells. Come back to your hyaline. You've got a good number of cells, you've got a decent amount of matrix, but a lot of cells in this picture. And a good number of cells also with elastic cartilage. And then you go to your fibrocartilage, and majority of what you're seeing is these wavy fibers. They're not accumulating kind of randomly, haphazardly around the cell, but they're going longitudinally, and that's a little bit different than the fibers in the elastic cartilage, where they're more of a disorganized array. These are designed to resist compression and prevent bone-to-bone contact. So you'll find those in meniscus, or you'll find those in your fibrous cartilage ring in your discs. So pads in the knee, those will be the meniscus in your knee. And then the intervertebral discs, pubic symphysis. If you're going to have children, or if you've had children, you know you don't want bone on bone, because if bone comes in contact with bone here, it ossifies. If you're going to try and get a baby that's 8 pounds or maybe more through that birth canal, you want things to soften and stretch. You can do that with a hormone that will soften this fibrocartilage, and you get some stretch there, so it's easier on you when you're delivering a baby vaginally. So it resists compression normally when you're weight bearing and you don't have this relaxin hormone that's softening the cartilage. It's helping to resist the compressive forces of your weight bearing and limit the movement. You don't want your pelvis moving up and down as you weight bear from side to side. Now, when you talk about this being softened and other ligaments and tendons being softened to accommodate the delivery of the baby, you don't want to be weight bearing very traumatically on those joints after to lose baby weight either. So we'll talk about that next semester. So cartilage is a supportive connective tissue. Bone is probably the most supportive. It's supposed to be mineralized so that it resists compressive forces the best. It also needs to be flexible. So you start out with collagen fibers, and if you're also for most cases attaching muscle to the bone. So you have your cartilage, your collagen for your bone. That's your rebar, but flexible rebar for your bone. You have your tendons, your connective tissue from the tendons inserting into the collagen. Then you have your osteoblasts mineralize everything together. And, well, blood vessels are there and all those other things too, but you have down here these Sharpie's fibers. Those are actually extensions of the connective tissue of your tendon. Those are going into the periosteum and then into the bone and anchoring the tendon there. You can exert a lot of force with muscle on your bone. You don't want the tendons ripping off the bone. So you start with the collagen, you mix in the connective tissue of your muscles, then you start depositing calcium salts. From the cells will start to deposit the calcium salts. So you're going to find that we'll talk more about bone, but you're going to see osteo, that's referring to bone. The cell that forms bone is an osteoblast. Once it's surrounded by its own matrix, then it's an osteocyte. Got carried away there. Cyte. So we have osteocytes in a lacunae. We're going to see that on the next slide. Osteocytes will surround themselves by their own matrix. So early when they're osteoblasts, they have to hook up with each other and form gap junctions so that they can share nutrients and clear waste products from each other. So a little confused now, you'll see, I'll explain it on the next slide. To separate the bone from the muscle, to separate the bone from other structures, you partition with a periosteum. Periosteum also helps to anchor things to the bone. So periosteum, peri means around. So peri, around. Don't confuse it with para, which means next to. Sounds similar but different. So peri, all the way around the bone. It's going to cover the surface of the bone, but it's going to stay away from joint cavities and articular surfaces. So it's not going to touch the cartilage. It's not going to extend over into the flexible part of your joint. So what do you want to attach to the bone? Blood vessels, nerves, lymphatics. You want to have those there and not moving away or being pulled away by movement of the tissues above. So you make a periosteum. The outer layer is fibrous, and your tendon fibers will insert into that, and then also into the collagen fibers, and they get mineralized by the calcium salts and anchor. The fibrous layer acts as a binding site for all these other things. On the inside, you have another layer that's cellular. This is where you have all the stem cells that are going to be important should you break a bone and need to heal a bone. You have everything there that is going to help you to heal that bone. So you think, okay, I need osteoblasts to fill in the gap of the fracture. You need more than that, because first you're going to, after you clear out all the debris, you're going to have to put down a cartilage model. Then you're going to have to ossify that with your osteoblasts. At the same time, you want to have, as you're laying down the cartilage, as you're laying down the bone, you want blood vessels to be in the bone because they were there before you damaged it. You want them to be there now in the healing bone. So you need stem cells for blood cells. You need stem cells for cartilage. You need stem cells for bone. Most bones in adults aren't making red and white blood cells anymore. They store fat. So you have a stem cell for an adipocyte that will replace the fat in the area that was damaged. And then you have to, if the break damaged the fibrous layer, you gotta have fibroblasts to repair that. So these cells that are called osteoprogenitor, it's not just the bone that you have to repair. You gotta repair the blood vessels, you have to make a cartilage model first, then you have to ossify it, and ossify it on the outside, the cartilage dies, then you can make blood cells, blood vessels penetrate. So you need all that. You need pericytes, adipocytes, fibroblasts, osteoblasts, and some getting chondroblasts. So they're all out there participating in the cellular repair. Different growth factors will then cause these stem cells to differentiate into different cell lines. There are some stem cells out there that always and only will turn into osteoblasts. But there are these others that can turn into anything depending on the growth factor at the time. Okay, so early on, osteoblasts form gap junctions with their neighbor. They're going to form just a few gap junctions here in the spongy bone. Spongy bone, if you're not familiar with that term, it's also trabecular bone. It's also sometimes called woven bone. It's in the center, so it's called medullary bone. There's a lot of different terms that you can use to describe that. So your text is calling it spongy bone right here. But the strut-like structures form columns, so trabecular bone, I think if you take Dr. Prince's class, he uses trabecular bone. At least he used to. Out here you have what's called compact bone. Compact bone is also called dense bone. It also is on the outside of the bone, so it's called cortical bone. So the inside was called medullary, and this is then cortical bone. So different terms to describe it. They're actually functionally different. Here you have a few osteocytes now that they've surrounded themselves by matrix. Early on, they were a few osteoblasts. They form a couple layers here, but they form multiple layers out here. The layers out here are surrounding a blood vessel. Well, two blood vessels, an artery and a nerve, and there's lymphatics there as well. So 3 vessels in the center. they will form what's called an osteon structure. We'll learn more about that when we get to the bone chapter. But these are concentric rings of bone. So they've dissected out a way so you can see the innermost layer, and then the next layer, they've just taken part of that away, and then take part of the outer layer away, and you can see that they're concentric rings. In order for the cells in these outer layers to get nutrients, when they've already surrounded themselves by mineral matrix, it's not going to happen by diffusion. So they have to have, not through the matrix anyway, so the diffusion has to come through the cell in the layer that's internal to it. And then that layer has to get it from the cells that are internal to it. And the one that's closest to the blood vessel picks up the nutrients and through the gap junctions passes it to the outer layers, and the waste products go in the opposite direction. So these will collect waste products from the outer rings and then give it to the venous system. So this is an osteon structure. So osteo with an N on it. We put osteon. So osteo and then N. That's the basic structure of your cortical bone, your compact bone. And then you have these little spicules or little projections of bone that form the spongy bone. The previous slide says that you have osteocytes in a lacuna, or lacunae, plural. So osteocytes has to be plural. So here's osteocytes in their little spaces. That's the cell body is in the lacunae, which is this little opening in the bone. And then they have processes that extend out before the mineral is secreted, and then the mineral is secreted to such a point that each of the processes is surrounded by a matrix, and what's left is a channel that is due to the deposition of the matrix around these cellular processes. Those channels are called canaliculi, which means small little canals. In your lab textbook, if you have the lab manual, look up the picture that shows you a super high EM magnification of those cellular projections that come together and form a gap junction. So somewhere out here in this bony matrix, you've got to have gap junctions formed by those cells. So you take the bone, you make a thin section, and then you start grinding it. And the bone dust goes everywhere. It goes on you, it goes on your glasses. It goes into these little openings in the bone. So over here, you've got brown bone. And where the bone dust collects in the lacunae, you get this black dot. And it kind of goes around in a ring. And then another layer of lacunae up external to that, where you have these little hair-like threads, black threads. Those are, that's the bone that's collecting in the canaliculi. So you don't clean that out, you use the bone dust to show to catch more mineral and show you these openings in the bone. The solid bone, where the mineral matrix is secreted, that won't pick up as much of the metals. So you can take a transmission electron micrograph, shine light through this dusting of heavy metal on the tissue, and you see the canaliculi, you see the lacunae. You also see where there was tissue that's sort of also dehydrated. Then the blood vessel, at least one blood vessel kind of shows up clearly there. So osteon is the basic structure of the cortical bone. you're always remodeling your bone. Throughout your life, I think it says every 17 years you have an entirely new skeletal system. So what they radio label the bone, and they see that all that radio label is gone in 17 years. That means you have replaced all those minerals over time. You look at the shape of your bones, they change. The density of your bones change. If you have a good exercise program that's stressing your bones, they tend to get denser. If you are a couch potato and you are not using your bones, and if your diet also is not good at getting calcium in, you start robbing calcium from your bones, they become thinner and more brittle and subject to fracturing. So cortical bone is actually good for anti-gravity forces, but if you hit it from an angle, it will shatter. So you have a car accident and your long bones run into the dashboard, usually end up fracturing those bones. There is a layer on a circumferential layer of bone all the way around the shaft of the bone. It's different than the osteon structures. These are called circumferential lamella. You'll see that in the bone chapter. Then you have the cellular layer of your periosteum and then the fibrous layer of your periosteum. Membranes, we've got mucous membranes. We've talked about some of those already. They're designed to have mucus secreted on their surface. This mucous membrane has a goblet cell that's producing the mucus. Other mucous membranes may have another cell that's producing the mucus. The secretion has to be wet enough so that it can be moved across the surface. Most mucous membranes are going to probably have cilia on the surface, and that will then move the mucus, which is there to trap particles that aren't supposed to get into your body. Will move the mucus and the trapped particles usually to an opening where you can either blow it out, spit it out, or swallow it and then fry it in your stomach acid. A serous membrane is, we talked about the visceral pleura on your lungs, parietal pleura on your chest wall. These are designed to put primarily water. They absorb fluids from the blood, and then they modify it and then secrete it on the surface. And that may be just to create a nice watery lining, but you might, in the case of your pleura, your peritoneum, your pericardium, have another serous membrane right next to it. So the transudate being mostly water, you have the properties of water acting for you. You have the adhesive property where it sticks to your chest, your parietal peritoneum, and it sticks to your visceral peritoneum. And then you have the ability for the intestinal structures to slide over each other. You come up to the pleura, the cohesive forces help you to expand the lungs. You use your muscles to bring your chest wall out and your diaphragm down to increase the volume so pressure goes down in your lungs and suck air in. You won't have the lungs expanding if you break that watery cohesive attachment between the two serous membranes. If air gets in there, if blood gets in there, then the lung will collapse. Chest wall may go out, the lung's not coming with it. So you need that water that from the transudate for those functions of your organs. Cutaneous membranes, that's your skin. That's designed for anti-friction, so you can scratch, and usually you're left intact. You have a barrier to water leaving your body. One of the really bad things about burns is they dehydrate so severely. You have to watch their fluid and their electrolyte balance, because that will screw them up more than the actual burn does. Also, if you take a bubble bath, you don't want to blow up like a sponge or just absorb water. So it's a barrier for water getting into you as well. Tends to be thick, thickest on the palms of your hands and soles of your feet. Relatively dry because of the dead layers of cells on the top. And then you get to synovial membranes. So you'll find synovial membranes on the inner surface of the joint capsule on all your freely movable joints. But you also find synovial membranes that form your bursa, that protect bone-bone contact from happening, and also around your tendons. So when you contract and use your muscles a lot, and the tendon is pulling on your bones a lot, you don't get an inflammation of your tendon. Of course, overuse, you get tendonitis because the synovial membrane is getting dried out. So synovial membranes, they will secrete synovial fluid. Synovial fluid is about the consistency of egg white. Very similar. You play with egg whites, and then you go and you play with your synovial membrane. You try and pick up the egg white, it kind of slips between your fingers, and it's very stringily attached to the rest of the egg white. Same thing with synovial fluid. You pull on it, it tends to want to slip and go back to its other attachment. In olden days, they actually used to take synovial fluid and put it between your fingers and pull their fingers apart quickly. And based on when that filament snapped, they could tell whether the synovial membrane was, synovial fluid was normal or not. So it's so cohesive that when you pull your fingers apart, you can get your fingers about 2 inches apart before that filament snaps. But if you have any osteoarthritis or other kind of inflammatory problem going on in your joint, you get about 1/4 inch apart and it's snapped already. So you get severe changes in that synovial fluid. The membrane secretes the fluid into the joint space. Your cartilage isn't really that far apart. It's in contact with the cartilage on the other side. You don't have this big space filled with synovial fluid. So this is an artist's misrepresentation of what's going on there. Synovial fluid gets nutrients from the blood supply and puts it out in contact with the cartilage. When you weight bear, the old stuff that went into the cartilage gets squished out, and when you take weight off your cartilage, then it will suck good stuff in. So if you want to keep your joints healthy, you must exercise. You must have weight-bearing exercises. It's an incomplete lining, so there's gaps. There's cuboidal cells here, and then little gaps in the membrane. And we'll talk more about that when we get to the importance of that when we get into arthritis changes. So body wall, they've taken a section out of this guy's chest. So they got skin on the outer surface. And then on the very inside, you've got a serous membrane. So it's in the thoracic area, so this would be your parietal pleura. That's that serous membrane. Here we're talking about connective tissue, specifically the fascia layers. Go back to your embryology and you look at that funny little pink thing that has the neural tube folding and zipping up, and then lateral to that fold that's zipping up, you have the little bumps there. They're labeled somites. Those are going to form your muscle and your bones. Also connective tissue. They're going to migrate around that developing embryo, and in the chest area, they're coming around the bones, your ribs. The ribs are shown there. The muscle layers, your internal, external, intercostals are actually more muscle layers, but primarily out here it's external and internal intercostals. So they're growing out, the skin's growing around, and you get fascia following the muscle and the bone development. So under the skin, you look at it and you say, well, that looks like fat. But they're calling it fascia because it is a connective tissue, and fascia is connective tissue. They're calling it here superficial fascia, but down here they're calling it the hypodermis. So below the dermis, that's where your superficial fascia is. It is the most superficial of all these fascial layers. So either way you want to describe it is correct. If you call it hypodermis, then maybe you want to call it that because you've got a hypodermic needle and you want to get whatever is in that syringe into the hypodermis. So you're not going to get it in there with a skinny little needle. You're going to need a big long needle to get through the dermis and into the superficial fascia. If you're talking about the other fascias and you want to say this is the most superficial, then you can use that term. The next layer, these two layers, they're labeled deep fascia. They're around the outermost layer of muscle, and there's another one around this next layer. So there's a shared layer of deep fascia between the two muscle layers, and then there's fascia that is around on the outer surface of both the two layers. So these are a lot of collagen. They're dense connective tissue. You want them to be able to stretch a little bit, but not a lot. So you're probably going to have dense, irregular connective tissue there, not dense, regular, which would be limiting the stretchability. This is also going to be present, the dense regular will be in tendons and ligaments, but the deep fascia will bind the tendons, go around the tendons and ligaments, and help to form the capsules around your joints. Innermost layer, you can call it deep fascia, you won't be wrong, but if you want somebody to go directly to that point and not be thinking, well, what deep fascia layer are you talking about? Call that the subserosal fascia. So the reference point now is your serous membrane, and this is underneath the serous membrane. So if you say, I want you to go look at the subserosal fascia, they go to the most inner layer of the deep fascia. They don't have to work their way in to figure out, oh, that's where you want me to go. So that would be a reason for using the term subserosal as opposed to deep fascia. But you could say, yeah, go look at the innermost deep fascial layer. But it's a little clearer and faster to get them oriented if you say subserosal. You're not wrong if you use the other term, but it's a little bit faster if you use subserosal. So subserosal fascia, a little bit different in that it's areolar tissue. So areolar is going to allow blood vessels and nerves and lymphatics to be present. If you have dense, irregular tissue, you're not going to get blood vessels, nerves, and lymphatics at a high concentration there. But you don't need to, because these deep fascial layers are there to partition, to help attach muscle to other muscle, and also to attach muscle to bone where it has contact with it. So different functions here. Muscle, just right now, we're going to be talking a lot about skeletal muscle in the muscle chapter. And we'll talk somewhat about cardiac muscle, more about cardiac muscle next semester, and more about smooth muscle next semester. I used to think, why do they devote a whole chapter to skeletal muscle and not a whole chapter to the heart muscle and the smooth muscle? And my conclusion was, it must be boring to talk about the others. Actually, it's that they didn't understand that much about them because they're such small cells, so they're much harder to visualize and study. If you look at the magnification here for skeletal muscle, 100 magnified 180 times, you don't even see the whole cell. This is just a very little part of the cell, and muscle cells can be as long as the sartorius. So it starts here, it ends here, and the fibers can be that long. So a couple feet long in me, taller people, they're even longer than that. They can be short too, but they can be very, very long. When skeletal muscles form, you get multiple nuclei. They've pretty much for sure shown myoblasts fuse and form these huge cells. So it's not one cell with multiple nuclei, it's multiple cells that fuse to form a cell. Skeletal muscle will get its actin and myosin and organize it very specifically to form sarcomere structures. Everything that's needed for the interaction of actin and myosin will be right next to these contractile filaments. So you have mitochondria for ATP production. You have to have calcium present when you want the muscle to contract, but you don't want it present when you don't want the muscle to contract. So you need to sequester the calcium. You put it in a smooth endoplasmic reticulum and store it there. So that's around the muscle fibers. But everything else is pushed off to the periphery, including the nucleus. So in skeletal muscle, the nuclei will be in the periphery. That's one of its characteristics. Another is that it has cross striations due to the high organization of the actin and myosin contractile filaments. And also it's huge. Only found in the skeleton. It's only found in it's found in your skeletal muscle that's moving your joints, but also it's found where you have sphincters. So mostly attached to skin when you want to close your eyes, all attached to skin in the mouth, all attached to skin at the anus, all attached to skin at the urethra. So sphincters that you have conscious control of. You can close your eyes on will, close your mouth on will, close your urethra, close your anus, and override sphincters that are not under your conscious control. It also generates heat. If you get cold, you shiver. You're not moving your joints, but the muscles are contracting out of synchrony to get that heat generated. Look at the magnification, 450. So the other one was 180. To see cardiac muscle cells, or at least the most of a cell, you have to increase the magnification about 4 times. You won't see the detail if you look at cardiac muscle at 180. You'll see some things like the dark bands of the intercalated disc, but you're not going to see the details as well as the higher magnification. So like your cardiac, like your skeletal muscle, you have these bands of actin and myosin, highly organized to form sarcomeres. You have at those attachments called intercalated discs. Intercalation means that the cells are interdigitating. So one cell goes into another in this fashion. There's desmosomal attachments at these intercalated discs that keeps the cells tightly attached to each other. And also in those areas, there's gap junctions. Gap junction this time is not passing nutrients. It's passing electrical charge from one cell to the next. The intercalated discs are keeping the cells attached together because this cell is on this side is contracting towards the nucleus, on this side is contracting towards the nucleus, but this guy is contracting towards its nucleus. So these two cells are pulling away from each other. If they're not tightly bound together, they simply come apart. Your heart no longer functions as a pump, and you're dead. Another difference from skeletal muscle, you can see almost a whole cell here at this magnification 4 times greater than what you looked at skeletal muscle where you couldn't see the whole cell. So these are small cells. They only have one nucleus. The nucleus is not in the periphery, it's in the center. The cells also branch. So you got branching, central nucleus, single nucleus, intercalated discs with desmosomes and gap junctions. Those are all different than skeletal muscle. Cardiac myocytes can regenerate. So change that in your PowerPoints. I forgot to change it, so I saw it yesterday and oh my gosh, another time I forgot to change this. Used to think cardiac cells did not regenerate because what they were looking at in heart attacks were big time damage. Now with the ability to look at enzymes that show up in the blood that indicate cardiac cells have ruptured, the lactic acid dehydrogenase of your cardiac muscle shows up in your blood, they know you've had a heart attack. Based on the concentration, they know how severe it was. When you have small heart attacks, the stem cells can replace the cells. When you look at the tissue, you see no effect of that heart attack. But if it's a big heart attack and a lot of cells have died, usually the fibroblasts get connective tissue in the area before the cardiac muscle can replace itself. So you end up with a patch of connective tissue that's non-functional as part of your heart. The myocytes that form cardiac muscle cells form everything in your heart. Your textbooks will show things that look like nerves in your heart, but there are no nerves in your heart. Conduction pathway in your heart is myocyte. Your pacemaker cells are modified myocytes. The cells that contract are myocytes. So everything that your heart does may be influenced by external nerves, but everything that goes on within the heart is all due to changes in myocytes. Smooth muscle, here the magnification is half of what the cardiac was, but it's sufficient that you're seeing most of a smooth muscle cell. You can see that it tapers at the end. So another name for smooth muscle is a spindle-shaped cell. Again, a centrally located nucleus, 1 per cell. So similar to cardiac in that it's got 1 nucleus, but then different in every other way. No cross striations. The actin and myosin are not highly organized to form bands that stop light. They're highly organized for the function of smooth muscle, but not for showing up cross striations. The cells are very small, no cross striation. They can act, in certain areas they have their own pacemaker, smooth muscle cells. So in the GI system, your smooth muscle will contract whether or not the autonomic nervous system is attached to your GI system. So it has its own pace of contraction, albeit it's kind of erratic without the autonomic nervous system involvement, but it can function fine, contract and push things along without that nerve innervation. So it's acting as a pump, which is similar to the cardiac muscle, but it's not shoving things out into the circulatory system with big volume. It's just kind of mixing, turning, moving it a little bit down the road. In your urinary tract, in your reproductive tract, it's moving urine. The lining of your ureters will contract and push urine to your bladder. When your bladder fills, smooth muscle will help to push the urine out the urethra. Moving the sperm out of the epididymis into the vas deferens and then out into the, to be ejaculated, that's smooth muscle job. Getting the ova into the fallopian tube close to the uterus, that's smooth muscle's job. Changing the diameter of your respiratory tract, just smooth muscle job. Nerves influence the other tissues. You cannot contract skeletal muscle without your alpha motor neuron stimulating it to contract. Smooth muscle can react to hormones in the blood. Cardiac muscle can react to hormones in the blood. But skeletal muscle has to have an intact motor neuron. So you have a dedicated process going to the skeletal muscle that will cause it to contract. Not all neurons have axons. There are neurons in your central nervous system. Instead of having this long process, they would just have more of these short processes. So it looks like they have only dendrites. So the term to describe them is anaxonal, meaning no axons. But in fact, all of the processes on these neurons, any one of them could be an axon. Any one of them could act as a dendrite. So they can switch around and put information out in any direction. So they're actually more functional than one that has to go in a particular direction. Most of the cells in your central nervous system are neuroglial cells, supporting cells, phagocytic cells, providing nutrients, providing selective permeability to the blood to the access to the brain. We'll talk more about neural tissue later in the semester. You'll have a cell body, that's the soma with the nucleus there. You have processes going off. If you want to distinguish a neuron axon from a dendrite, you look for the rough endoplasmic reticulum. It will extend out into the dendrites, but it will not go out into the axon. That's how you do that distinction. Apoptosis. Ap, and then O, and then a silent P, pretty silent P, and then ptosis. So I've heard people say apoptosis. No, wrong. It's soft A, it's not a strong A. So apoptosis is a process of losing cells that genetically predetermined you no longer need, or time clock determined it's time for them to leave. But you don't want an inflammatory response taking these cells out of commission, because that potentially could harm healthy cells in the area. Inflammation requires chemicals to be released that are proteases, elastases, collagenases. So you're going to get a lot of damage if you have an inflammatory process happening. In apoptosis, they call it programmed cell death. Somewhere in the genome, these cells have been predetermined that their life is over, and so they just implode on themselves and become a little bleed that then is phagocytosed by an immune cell or a neighboring cell. So it's a very neat death. You don't damage any of the healthy cells in the area. How do you get fingers and toes to separate? Apoptosis. You watch the developing embryo, the fingers are fused, the toes are fused. But when the baby's born, they're free, they're movable. Actually, before birth, they're free and movable. But you've probably seen people who do have webbing that is greater than the normal. The fingers is extending up into the proximal phalangeal area. Makes for a very good swimmer because they got more surface area to pull the water, but it's kind of a strange looking hand, but it's functional. Some people get no apoptosis between the index and the middle and the ring and the little finger, and the skin is all the way around, so no indication that there's two bones in there. You do x-ray, there's two bones, but you look outside and it looks like they only have two big fat digits called a lobster claw deformity. All that happened is that you failed to get apoptosis there, so it didn't free up those two digits. So various things, your enterocytes, the lining of your GI tract, has a high turnover rate. You have a lot of things going by that are injuring these enterocytes on the surface. You got pH changes, you got fiber in your diet, you just simply age, they're going to have this programmed cell death, and stem cells will replace the surface cells. So enterocytes are there for a period of time, and then they're going to undergo this implosion, this apoptosis, and then new cells will replace them. If you've ever walked around or looked at pictures, looked at people in the media, you might see that somebody has an eye that isn't quite as big as the eye on the other side. It's not that the eyeball is different, it's that the slit is different. So there's less of an opening on one side than the other. Still failure of apoptosis on this side, normal apoptosis on that side. My favorite is Carol Burnett. I don't know if you're young enough or old enough to know who that is, but a comedian. So Google her. When she smiles, it's like her mouth is going towards her ears. It's a huge mouth, and she uses that to her advantage as a comedian, but big time apoptosis there. And other people, they have small little mouth. The daughter on Castle, if you watch Castle, she's got this cute, perky little mouth. Not very big at all, and it looks great on her face. But you think, it's a pretty small mouth. So, a little bit less apoptosis there. So anyways, stem cells. Stem cells are there to replace cells. Stem cells are there to form your whole body mixture. If you have totally potent cells, they call totipotent here. Those are the cells that can form any tissue in your body. Well, we lose those after they form the tissues in your body. They don't, at least they can't find them anymore in the body, or they haven't found them in the body. What they do find is the pluripotent cells, like the osteoprogenitor cells, that can form multiple cell lines. They can form 5 or 6 cell lines. Cells like the spermatogonia or the stem cells at the base of your epidermis, these are multipotent, but not pluripotent. If you get access to the umbilical cord, you're probably getting some cells that have greater capability of forming multiple tissues. Politically controversial. So some researchers are looking at the skin as a source. Their stem cells, maybe in the lab they can get them to become pluripotent again. Maybe they can make them become potent again. So research is looking into how you manipulate stem cells that you can easily access and maybe get them to form other things for replacement of worn out body parts. So repair, maintenance, you're going to get old too, you think you won't, but you will, and everything becomes less efficient. Your skin's production of epidermal cells gets less, your skin thins, your angiogenesis factors that form blood vessels, your capillaries get weaker, they burst more easily. Hormones change, muscle mass changes, hormones change, your skeletal mass changes. Some of that muscle and bone is due to activity level, but sometimes the change in the muscle mass changes your activity level, and then muscle mass changes in the negative direction, and your activity level gets less. So cardiac muscle, it can regenerate, so I've got to change that one, sorry about that. Minor damage, if it's corrected, should be no problem. If it's not fully corrected before the next little heart attack happens, and then you've got some residuals from that, and another heart attack happens, you finally get accumulation of all those small damages, and boom, you got big time heart attack. Muscular damage as well, you can have, I think, up to 50% or 49.9% rotator cuff damage and be asymptomatic. You get that 1% more damage, and all of a sudden the shoulder doesn't want to move and it's extremely painful. So you can accumulate a lot of damage before it's actually apparent that the damage has happened. So all this, the rest of this, we can go over. We've already gone over that with the other handout on embryology. This has a good word summary of what each of the layers in the embryo is going to end up forming. So use that for your review and stimulation of your understanding of what is formed by each of those layers. Okay, so take a break, and then we're going to go into